Many ABS systems today also have traction control capability. Traction control is similar to anti-lock braking, except that it occurs during acceleration rather than braking. The ABS traction control module uses the same inputs from the vehicle's wheel speed sensors to monitor wheel slippage during acceleration as well as braking. If the control module detects a difference in sensor readings between the vehicle's drive wheels or between the drive wheels and the non-drive wheels, it initiates traction control to minimize wheel spin. On applications where braking alone is used to control wheel spin, the ABS traction control module will apply hydraulic pressure to the brake on the wheel that's spinning. This will slow the wheel and transfer drive torque through the differential to the opposite wheel that has better traction. If both drive wheels are losing their grip, then both wheels will be braked to reduce wheel spin. Brake pressure is applied to the drive wheels by a pump. When the ABS control module determines that traction control is needed, it energizes the pump to apply pressure. Pump pressure is then routed to the brake circuit by opening a valve in the hydraulic modulator. The solenoid-actuated traction control valve is usually separate from the other ABS valves for the brake circuit. When brake pressure is applied, the brake circuit must be isolated from the rest of the system so pressure isn't applied where it isn't needed. This is done by closing the isolation valve when the traction control valve opens. Many traction control systems also employ other control strategies in addition to braking to minimize wheel spin during acceleration. These include reducing the engine's power output by reducing the engine's throttle opening. A throttle relaxer on the throttle linkage pushes back against the gas pedal to reduce the throttle opening and to let the driver know he should ease up on the pedal. Another technique is to reduce the engine's power output by momentarily retarding spark timing or killing some of the engine's fuel injectors. These functions are actually handled by the engine's control module, but are based on inputs from the ABS traction control module. Diagnosing and troubleshooting anti-lock brake systems can be a rather intimidating process, but it doesn't have to be, as long as you keep a few of the basics in mind. The most important of which is don't assume ABS is the problem. The majority of customer complaints on ABS-equipped vehicles will stem from conditions in the conventional part of the system. So think basics and give the vehicle a quick visual inspection and correct any obvious defects. Check brake fluid levels. If low, add .3 fluid to the proper level. If contaminated, replace with new .3 fluid. Never use silicon-based fluids in anti-lock systems. As a general rule, inadequate stopping, pulling to one side, a pulsating brake pedal during normal stopping, and grinding or squealing noises are not ABS related. Isolate the sources of these complaints and repair them as you would any non-ABS system. Remember, a non-ABS problem could be masking an ABS problem. So check out the ABS system before returning the vehicle to the customer. Once you've decided that there is indeed a problem in the ABS part of the system, 3 ideas will help you quickly locate the root cause of the problem. Keep in mind the overall concepts of how an ABS system works and the interrelationship of its components. Be systematic. Anti-lock brake systems are too complex to play hunches and take shortcuts. Being systematic requires discipline, but it does save time and leads to better repairs. Think basics. High-tech systems such as ABS tend to make most people look for exotic problems. A frayed wire or a broken sensor is much more likely than a damaged electronic control module. After interviewing the customer and verifying the complaint with a road test if appropriate, the best place to begin diagnosis is with the brake system warning lights. They can quickly point you in the right direction. Most vehicles equipped with ABS have an amber warning light on the instrument panel. This is in addition to the red warning light for the conventional braking system. When both lights come on at the same time, the problem is probably hydraulic in nature. If the amber light only comes on and the brakes operate normally, the problem is generally electronic or electrical. Ask your customer, when do the lights come on? This can give you clues. For example, suppose both lights go off after startup, but the ABS light comes on once the vehicle starts to move. In this instance, the problem is almost certainly in a wheel sensor. Once you've isolated whether the problem is most likely hydraulic or electrical, you can begin more sophisticated tests. That's a quick overview of the basics of ABS diagnosis and troubleshooting. Before we close, we want to remind you of some basic precautions to take whenever working on an ABS system. Precautions to protect the ABS electrical system include: don't arc weld with the computer plugged in. Don't fast charge the battery with the computer plugged in. Don't disconnect the battery while the engine's running. Don't expose electrical components to high heat. And don't position add-on equipment too close to ABS wiring. Failure to follow these hydraulic precautions could result in injury. On all integrated ABS systems, you must depressurize the accumulator by turning the ignition system off and depressing the brake pedal 40 firm applications. And never use any silicone brake fluid, .5 fluid, in any ABS systems. Always use .3 fluid. Since many common ABS faults are electrical problems, such as shorts, opens, grounds, loss of voltage, excessive resistance, and so on, this segment deals with electrical test procedures that are often necessary to pinpoint what's causing the problem. A digital volt-ohm meter is an essential piece of test equipment that can help you measure circuit voltages and resistance and check continuity. A digital volt-ohm meter is better than a test light, because it gives exact voltage and resistance readings, not just an indication of whether or not voltage or continuity is present. It's also better than an analog volt-ohm meter, because a 10 mega-ohm impedance digital volt-ohm meter provides a certain amount of protection against overloading sensitive electronic circuits, which can be damaged by test meters that lack the proper impedance. Another piece of test equipment that's essential for ABS diagnostic work is a breakout or pinout box. With the appropriate adapters, a breakout box can be plugged into the ABS control module wiring harness to provide easy access to all of the system circuits. Using a breakout box to check circuit voltages and resistance is a lot easier than trying to check each and every circuit at various points throughout the vehicle. Reading voltages and resistance at the breakout box is also a good way to test an entire circuit, not just an individual component. It will show you exactly what the control module is seeing in a particular circuit. Wheel speed sensor problems are a common ABS fault where a digital volt-ohm meter and breakout box come in handy. When a fault code for a wheel speed sensor is present, the typical shop manual diagnostic procedure usually involves a resistance check at the control module using a breakout box. This will tell you whether or not there's continuity in the circuit and whether or not the resistance at the wheel speed sensor is within specification. If the circuit reads open or resistance is out of specifications, the next step is to unplug the sensor and check its resistance. If the sensor's resistance is too high or too low, it's assumed to be defective and needs to be replaced. If the sensor checks out okay, however, then the wiring should be checked for continuity, shorts, grounds, or excessive resistance. If no sensor or wiring problems are found, the sensor and wiring are okay, and the problem is elsewhere. The next logical items to check are the sensor's air gap and the sensor ring. The air gap on adjustable wheel speed sensors is critical and must be set to specifications for an accurate speed signal. If the tip of the sensor is too far away from the sensor ring, the signal may be too weak for the ABS control module to read. If the sensor is set too close to the ring so that it scrapes the ring, it may be damaged. Wheel speed sensors are magnetic and can attract metallic debris. This can be just as much a problem, if not more of a problem, for speed sensors that are mounted in the differential or transmission. Metallic debris from normal gear and bearing wear, as well as metallic particles from automatic transmission clutch linings, can be carried by the oil to the sensor. As debris builds up on the sensor tip, it reduces the sensor's ability to generate a reliable signal. Removing and inspecting the sensor for this type of contamination, therefore, is recommended if a sensor problem is suspected. To produce an accurate signal, a wheel speed sensor also needs a sensor ring that is in good condition. Broken or damaged teeth will cause the sensor to miss a pulse every time the defective tooth passes under the sensor. Depending on the sensitivity of the ABS control module's self-diagnostics, this may or may not set a fault code. But either way, it will affect the accuracy of the signal. The sensor ring must also be the correct one for the application. The number of teeth must be correct for the system. When replacing brake rotors, hubs, or drive axle shafts on front-wheel drive cars, make sure that the replacement part has the proper sensor ring for the wheel speed sensor. Count and compare the number of teeth if necessary, and make sure the sensor ring is not damaged. Another useful tool for analyzing wheel speed sensors, as well as other ABS system inputs, is an oscilloscope. An oscilloscope allows you to see voltage signals as trace patterns rather than a digital reading. This has a couple of advantages over reading signals with a digital volt ohm meter. One is that it makes it easier to spot obvious problems. The other is that it allows you to detect transient problems that might never be detected by other means of testing. A wheel speed sensor produces an alternating current signal that appears as a sine wave on a scope. As the speed of the wheel changes, the frequency of the signal changes, causing the scope pattern to also change. If we spin the wheel faster by hand, you can see how speeding it up compresses the sine wave pattern produced by the wheel speed sensor. If we slow down the wheel, you can see how the pattern extends with more space between the waves. Observing the sensor pattern on a scope will quickly show you several things. It will tell you whether or not the sensor is producing a signal. It will give you an indication of the overall strength of the signal, which is shown by the height of the wave pattern. This, in turn, will tell you if the air gap is correct. Too wide an air gap will produce a weak signal that the ABS control module may not be able to read accurately. A weak signal may also be caused by a buildup of metallic debris on the tip of the sensor. Observing a sensor scope pattern will also tell you if there's a problem with the signal's profile. A wave pattern that is ragged or has missing humps would indicate a damaged sensor ring with missing or broken teeth. So a scope can reveal a lot of information very quickly about the performance of the wheel speed sensors. Computerized diagnostic equipment is also available that combines the capabilities of a scan tool with those of a digital volt ohm meter to help you identify and pinpoint ABS problems. In addition to retrieving and displaying fault codes, some equipment has the capability of analyzing sensor data and other system inputs to flag obvious faults. Some test equipment also has the capability to perform various ABS system performance checks. One such test is to check the operation of the ABS solenoid valves in the hydraulic modulator. By energizing the isolation valve solenoid for a particular wheel circuit, you can determine whether or not the isolation valve is closing off the circuit. If the wheel turns freely while the isolation valve solenoid is energized and pressure is applied to the brake pedal, it means the isolation valve is working properly. If the isolation valve is not closing or is not sealing tight, however, the wheel cannot be spun when the brakes are applied. Some equipment can also perform a simulated ABS stop right in the service bay to check the overall operation of the ABS system. This is done by feeding the ABS control module a simulated speed signal. When the brakes are applied, the control module thinks the wheels are locking up because they're not turning. It responds by initiating anti-lock braking and cycling the ABS solenoids through the three-step isolate, dump, reapply cycle. If the system is working properly, you should hear the familiar clicking or buzzing produced by the ABS solenoids, as well as feel feedback in the brake pedal. When replacing a wheel speed sensor, be sure to inspect the sensor ring for damaged or broken teeth. If the ring is defective, it too must be replaced. Also, inspect the wiring and connector. Make sure the connector fits tightly and is free from corrosion. Right and left, as well as front and rear sensors on many vehicles, are not interchangeable, so make sure you have the correct sensor for the application. Applying a thin coating of anti-seize compound or grease to the outside of the sensor will protect against corrosion and make the sensor easier to remove in the future. If a sensor is non-adjustable, simply install it and tighten its holding bracket or fasteners. On some applications, the sensor is an integral part of the wheel hub assembly and cannot be replaced separately. With adjustable wheel speed sensors, the air gap between the sensor tip and sensor ring must be set within certain tolerances, so the sensor will produce a reliable signal. Refer to a shop manual for the exact air gap specifications, because they vary from one vehicle to another, as well as from front to rear. The air gap should be set using a non-metallic feeler gauge, either brass or plastic. Insert the wheel speed sensor into its bracket or hole, and position it so the feeler gauge just fits between the sensor tip and sensor ring. Then tighten the sensor's bracket or fasteners and recheck the air gap to make sure it hasn't changed. Some wheel speed sensors come with a plastic tip or a thin piece of paper on the tip. The spacer provides the correct air gap and eliminates the need to use a feeler gauge to set the air gap. To install this type of wheel speed sensor, insert the sensor into its bracket or hole and push it until the tip just touches the sensor ring. Then tighten the bracket or fasteners to lock it in place. Before connecting the wheel speed sensor's wiring harness, apply dielectric grease to the connector terminals to protect against corrosion. Align the connector, then snap it together and make sure it's locked in place. Also, check to see that the wiring is properly supported and positioned away from moving parts or suspension components that may damage it. The brakes can be bled in the usual manner manually or with power bleeding equipment on most ABS applications. Just be sure to follow the particular wheel bleeding sequence recommended for the application. Failure to remove all the air from the brake lines can result in a soft or low pedal. It will also adversely affect the ABS system's ability to prevent wheel lockup during hard braking. If the master cylinder or hydraulic modulator has been replaced on a non-integral ABS system, or the master cylinder modulator assembly on an integral ABS system, a special bleeding procedure may be required to remove air from the ABS modulator, depending on the application. On some integral systems, such as Bendix 9 Jeep and Bendix 10 systems and Tevis Mark II, the modulator will bleed itself when the ignition is turned on, and the pump starts to run. On other ABS systems, bleeder screws are provided on the modulator for removing air from the unit. The exact bleeding procedure will vary depending on the application. So we'll look at a Delco Moraine PowerMaster 3 system to get an idea of what's involved. On the Delco PowerMaster 3 system, the accumulator must first be depressurized by pumping the brake pedal 40 times while the ignition is off. The pedal will feel noticeably harder when the accumulator has been fully discharged. Once this has been done, the front brakes are bled, starting with the right one first and then the left one. After the front brake lines have been bled, turn the ignition on to recharge the accumulator. Then bleed the rear brakes, starting with the right one, followed by the left one. After bleeding the rear lines, the isolation valves in the PowerMaster unit are bled by opening 2 bleeder screws on the unit. Light pedal pressure will force fluid through the screws to remove air. Only 1 screw should be bled at a time. Afterwards, depressurize the accumulator again by pumping the brake pedal 40 times with the ignition off. Wait about 2 minutes for the brake fluid to settle. Add fluid as needed to the fluid reservoir. Then reapply pedal pressure and turn the ignition on for 3 seconds, then off. Cycle the ignition on and off every 3 seconds 10 times to complete the bleeding procedure. On other applications, such as Kelsey Hayes 4WAL, a scan tool must be used to cycle the ABS solenoids in the modulator on and off to get air out of the unit. On Delco ABS 6 applications, a scan tool is also needed to home the rear pistons in the modulator. If this is not done, the rear brake lines cannot be bled. The rear pistons are returned to the home position by choosing the manual control mode from the ABS test menu, then commanding the rear motor to drive the pistons to their home position. The pistons can also be homed without a scan tool by driving the vehicle above 3 miles per hour. This causes the ABS module to reset the system by homing the rear displacement pistons.
In this video, we'll cover 3 anti-lock brake systems manufactured by the Bendix Corporation that you're likely to see in your shop. The first system is one that's used on 1989 and newer Jeep Cherokees and Wagoneers. Now, it's an integral anti-lock brake system that combines the master brake cylinder with the hydraulic control modulator and 2 accumulators. The pump and motor are a separate assembly, but work with the master cylinder and hydraulic modulator assembly to provide power assist as well as anti-lock braking. The second anti-lock system we'll cover in this video is Bendix 10, and it's used on 1990 and newer Chrysler New Yorker, Imperial, and Dodge Dynasty models, as well as 1991 Dodge Caravan and Plymouth Voyager minivans. Now, like the Jeep system, Bendix 10 also uses an integral master cylinder and hydraulic modulator assembly with a remote pump and motor for power assist and anti-lock braking.
The third ABS system we're going to look at is Bendix 6. It's found on 1991 and up Chrysler LeBaron, Dodge Daytona, Dodge Spirit, Plymouth Acclaim, and Plymouth Laser models.
Unlike the other 2 Bendix ABS systems, Bendix 6 is an add-on or non-integral ABS system. It has a conventional master brake cylinder and power booster with a separate hydraulic control modulator for anti-lock braking. Let's start by taking a closer look at the Bendix system that's used on the Jeep applications. The Bendix ABS system that's found on the Cherokee and Wagoneer is the only other ABS system besides the Kelsey Hayes 4-wall system that works with 4-wheel drive. Now, the Bendix Jeep ABS system has an unusual feature compared to other ABS systems in that it doesn't become functional until the vehicle's speed reaches 12 to 15 miles per hour. It's also designed to disengage at speeds below 3 to 5 miles per hour, which may allow the wheels to chirp or skid slightly just before the vehicle comes to a complete stop when braking hard. Now, this is a normal condition for this system and does not indicate a problem. It was designed to function this way to make it more compatible with select-track four-wheel drive. Let's look at the major components in this ABS system, starting with the wheel speed sensors.
There are 4 wheel speed sensors, one for each wheel. The front sensors are located on the steering knuckles, with the sensor rings mounted on the axle shaft. The rear sensors are mounted on the rear brake backing plates and the sensor rings mounted on the axles. Like other ABS wheel speed sensors, magnetic induction produces an alternating voltage signal whose frequency varies in direct proportion to the vehicle's speed. This signal is converted into a DC voltage signal before it's processed by the electronic controller. It's important to remember that mismatched tires or tires that are a different size than the original will affect wheel speed sensor readings and may upset the operation of the anti-lock brake system. Replacement sensors may come with a polyethylene strip on the pickup end of the sensor. This strip is the exact thickness needed to automatically set the air gap when the sensor is installed. The sensor should be positioned so the strip just touches the sensor ring, then back it off so it just clears the ring. A non-magnetic brass or plastic feeler gauge can also be used to set the air gap. The air gaps on these wheel speed sensors are adjustable, and a proper gap is essential for a good signal. The recommended gap for the front sensors is 13 to 19 thousandths of an inch. The gap in the rear should be 30 to 36 thousandths of an inch. The brains of the ABS system is the electronic controller. You'll find it under the back seat attached to the floor pan. On 1989 and 90 models, the mounting angle of the controller is important because it contains a mercury switch that monitors vehicle deceleration.
Now, the integral master cylinder, hydraulic control modulator, and accumulator assembly contains a number of components with which you should be familiar. So let's start with the switches first.
There's a boost pressure differential switch mounted on the pressure modulator. It has a single terminal, is self-grounding, and is normally open. This switch performs the same function as a differential pressure switch in a conventional brake system. If a leak anywhere in the brake system allows loss of pressure, the difference in pressure between the primary and secondary sides of the hydraulics pushes the switch to one side and grounds it. This signals the controller that something is amiss. The controller then illuminates both the red brake warning light and the yellow ABS warning light and disables the ABS system. There's also a brake proportioning valve and switch, which are similar to other proportioning valves, and an accumulator low pressure switch for signaling the controller if accumulator pressure is lost. The accumulator switch is also a one-terminal self-grounding switch that stays closed during normal operation. If pressure in the accumulator drops below 1050 psi, the switch opens and the controller illuminates the yellow ABS light. If accumulator pressure does not increase enough to close the switch within 20 seconds, the red brake warning light will also come on. The 3 switches we've just described, plus a small filter located under the reservoir filler cap, can all be serviced separately. Be sure to check and clean the filter when doing brake work on this system. This ABS system will contain 2 accumulators. The first one is a high-pressure accumulator that is nitrogen pre-charged to 1000 psi and is designed to store fluid at 1700 to 2000 psi. This accumulator is located on the master cylinder booster assembly. The second accumulator might be called a low-pressure reservoir because it is nitrogen pre-charged to only 350 psi. But it can also store fluid at 1700 to 2000 psi. This accumulator is located next to the pump motor.
To protect the system from serious damage that would be caused by too much pressure, there's a pressure relief valve and thermal fuse. The pressure relief valve is a simple blow-off valve that opens if pump pressure exceeds 3000 psi. The relief valve does not reseat if it's been forced open and must be replaced. The thermal fuse will shut the pump off if the pump's operating temperature exceeds approximately 385 degrees. In this segment, we'll look at the Bendix 10 ABS system that was introduced in 1990 on the Chrysler New Yorker, Imperial, and Dodge Dynasty models, and the 91 Dodge Caravan and Plymouth Voyager minivans. Now, like the Jeep system we've previously covered, Bendix 10 also uses an integral master cylinder and hydraulic modulator assembly with a remote pump and motor for power assist and anti-lock braking. It also has 4 wheel speed sensors, all of which are non-adjustable. The tone wheel for the front sensors is located on the outboard constant velocity joint housing, which means the CV joint has to be replaced if the ring is damaged. Like the Jeep application, the Bendix 10 system also divides the brake system into 3 channels for anti-lock braking. The front brakes are controlled independently, while the rear brakes are controlled as a pair. It's called Bendix 10 because the hydraulic modulator contains 10 solenoid valves. There are 4 isolation solenoid valves, 1 for each wheel, and 3 decay and 3 build valves for each of the front brakes and both rear brakes. The extra isolation solenoid in this system helps reduce pedal pulsation and feedback during anti-lock braking.
Like the Jeep ABS system, it will also have 2 accumulators. The accumulator located on the master booster assembly is pre-charged with nitrogen to 1,000 psi and has a normal operating pressure range of 1,600 to 2,000 psi. The accumulator is a serviceable item, but it must be depressurized prior to removal by applying the brakes 40 times with a key off. A second low-pressure accumulator that's pre-charged to 460 psi and uses a sliding piston rather than a diaphragm is located on the pump motor assembly. Other components on the modulator include a dual-function pressure switch. It's located on the bottom of the modulator. It turns the remote pump motor on and off by grounding the pump motor relay through the starter solenoid. The switch maintains accumulator pressure by turning the pump on when the pressure drops below 1,600 psi and off when pressure reaches 2,000 psi. Like the Jeep system, this switch also warns the controller if accumulator pressure drops below 1,000 psi. When the switch opens, the red brake and yellow ABS warning lights are illuminated, and the ABS system is disabled. A fault code is set if the problem doesn't go away within 2 minutes. There's also a differential pressure switch to detect pressure differences of more than 300 psi between the primary and secondary sides of the brake hydraulics. A problem here will illuminate both warning lights. 2 pressure transducers are also used in the Bendix 10 system on the modulator assembly to detect pressure problems. Each generates a voltage of 0.25 to 5 volts that is proportional to the amount of pressure. One monitors boost pressure and is located on the bottom of the modulator assembly. The other monitors primary pressure in the master cylinder and is located on the left side of the hydraulic assembly. A fluid level switch on the reservoir keeps an eye on the fluid level. The switch consists of a float and magnetic reed switch which closes when the fluid level is too low. This will illuminate both warning lights and disable the ABS system. The controller in vehicles with the Bendix 10 system is usually found under the battery tray. Power to the controller is provided through a relay in the power distribution center located on the left side of the engine compartment.
Unlike the Jeep and Bendix 10 ABS systems that we've just described, the Bendix 6 system is an add-on or non-integral anti-lock brake system. It uses a standard master cylinder and vacuum booster with a separate hydraulic modulator, pump motor, and accumulator assembly located on the frame rail. Bendix 6 has 4 non-adjustable wheel speed sensors. Like the Bendix 10 system, the front sensor tone rings are on the outboard CV joints. The system is called Bendix 6 because the modulator assembly contains 6 solenoids. There are only 2 isolation solenoid valves, one for the primary side of the hydraulic system and one for the secondary side. The isolation valves are activated when the controller determines that anti-lock braking is needed at either front wheel. Like the Bendix 10 and Jeep applications, Bendix 6 is a 3-circuit ABS system. The front brakes are controlled individually, while both rear brakes are controlled as a pair. So the build decay solenoids for the rear brakes are actuated simultaneously.
Bosch anti-lock brake systems are used on a wide variety of vehicles, both domestic and imported. In fact, probably no other ABS system has a wider range of applications. Manufactured by the Robert Bosch Company in Germany, applications for the various configurations include sports cars, such as the Corvette and Porsche, family vehicles, such as the Dodge Dynasty, Buick Reatta, and Toyota, and luxury applications, including Mercedes-Benz, Cadillac Elante, and even Rolls-Royce. In spite of the wide range of Bosch applications, all Bosch systems have much in common. They're based on similar components, system layouts, and operating principles. In fact, there are only 4 system designations to cover all Bosch applications. 3 of these are non-integrated, or add-on types: Bosch 2, Bosch 2S Micro, and Bosch 2U. The Bosch 3 is a fully integrated ABS system. Of the 4 Bosch ABS configurations, the Bosch 2 has the widest range of applications. And since it's been around the longest, beginning in 1981 on the Mercedes and on the Corvette in 1986, it's also the one you're most likely to work on. The Bosch 2 is in many ways the basis for the entire Bosch ABS lineup. If you understand its components, then it's easy to understand each of the other configurations by how it differs from the Bosch 2. The Bosch 2 consists of toothed tone rings, which, depending on the vehicle, can be located at each wheel or at each front wheel and on the rear axle or differential. There are also 3 or 4 corresponding wheel speed sensors, depending on whether the vehicle has 3 or 4 ABS channels. The very small distance between the sensor and wheel teeth is called the air gap. This can be adjusted on some vehicles, and on others it's set at the factory. An electronic control module is the brains of the system. It's often called simply the controller, electronic brake control module, or the common acronym EBCM. It can be located under the hood, in the trunk, or, as on this Corvette, behind a rear seat. An amber ABS warning light is typically located on the vehicle's instrument panel. This is in addition to the red non-ABS warning light for the conventional braking system. The sequence in which these 2 lights come on and go off can provide diagnostic clues. The system includes an ABS diode, which functions as an electronic check valve to help prevent EBCM damage should voltage be introduced on the wrong side of the circuit. This could happen if an electronic component fails or there's a short in the circuit. The system's hydraulic modulator contains 3 solenoid valves. Each valve is a normally open 3-position spring-loaded valve. 2 solenoid valves control the front calipers. The other valve controls the rear. The modulator also contains the electric motor and pump assembly and 2 accumulators. In addition, 2 vehicles have special adaptations to the basic Bosch 2 system. The 1986 to 1989 Corvette featured a lateral acceleration switch. Toyota all-track models have a deceleration sensor. Essentially, the Bosch 2U system differs from the Bosch 2 system in 3 ways. The Bosch 2U has a different modulator design. Although it provides the same functions as the Bosch 2 modulator, the 2 units cannot be interchanged. Generally, Bosch 2U systems use only 3 wheel speed sensors. The single-speed sensor on the rear-wheel drive vehicles is located in the differential and monitors the average axle speed to measure rear-wheel activity. Front-wheel drive applications use 4 sensors. Rear sensors are at each wheel, and front sensors are in the steering knuckles. The Bosch 2U electronic control module is more advanced than that on the Bosch 2. It's able to generate diagnostic fault codes, and eliminates the need for a dedicated ABS tester. The Bosch 2S Micro is found only on 1990 and 1991 Corvettes. It differs from the Bosch 2 found in earlier Corvette models in 3 ways. The electronic brake control module is located in the small compartment behind the driver's seat. As with other Bosch 2U applications, it generates fault codes, which a technician can access using a manual flash code procedure or with a scan tool. As with earlier Corvette ABS applications, wheel speed sensors are located at each wheel. The rear wheel sensors are not interchangeable, and the wheel or tone rings are not serviceable and must be replaced if damaged. Front wheel sensors are part of the wheel and hub assembly. The sensor is not replaceable, nor is the air gap between the sensor and ring adjustable. The Bosch 2S Micro is equipped with a lateral acceleration sensor rather than a switch as in previous Corvette applications. The sensor permits a graduated reading of progressively higher side loads. The switch simply opened and closed when side loads of over 0.6 Gs were encountered. Unlike Bosch 2, 2S, and 2U, the Bosch 3 ABS is a totally integrated anti-lock brake system. This means the master cylinder, hydraulic modulator, and high-pressure pump and accumulator are combined into a single unit. Bosch 3 is an integrated 4-channel system. The hydraulic modulator has 4 3-way solenoid valves, which control each circuit independently during anti-lock braking. This permits greater rear brake control than is possible with 3-channel systems such as Bosch 2. There's a wheel sensor at each wheel. Typically, front sensors are located on the outer constant velocity joint housing. The rear sensors are an integral part of the rear hub bearing assembly. If replacing a front-wheel drive shaft, make certain that the replacement shaft has the correct outboard constant velocity joint with the sensor ring. The adjustability of the air gap varies by application. The Bosch 3 electronic control module is configured for 4-channel operation rather than 3 as with Bosch 2 units. Location of units vary by application. Since some applications have identical connectors, care must be taken that the right module for the application is being used. The hydraulic unit integrates the functions of the modulator, master cylinder, and booster assembly. It's the heart of the Bosch 3 ABS system and contains several components and sub-assemblies. The master cylinder is located in the upper portion of the unit. It works in the usual way, except that pressure is stored in an accumulator rather than by the mechanical assistance of a vacuum booster. The accumulator is mounted upright on the right side of the hydraulic unit and looks like a small cylinder. Be careful when working with this part of the system, as pressure can exceed 2,500 pounds per square inch. The reed block assembly is located in the master cylinder assembly and contains 2 switches for keeping the control module informed about the position of the booster piston. The valve block is attached to the master cylinder and contains the 4 3-way solenoid valves. The pump motor assembly and relay is the last major component of the hydraulic unit. It creates the hydraulic pressure that is necessary to charge the accumulator for normal braking, anti-lock braking, and traction control braking. That concludes our brief look at the components which make up the Bosch anti-lock brake systems. The systems, while markedly different, share many things in common. Understanding the relationship between the systems can be of great value in diagnosing and repairing any anti-lock brake system.
The Delco PowerMaster 3 system was used on the 1989 through 91 Buick Regal, Olds Cutlass, and Pontiac Grand Prix and GTU models. It's currently used only on Lotus Esprit. Now, unlike the Delco 6 system, PowerMaster 3 is an integral ABS system. It uses a high-pressure pump and an accumulator for power assist as well as for anti-lock braking. It's functionally similar to other integral ABS systems, such as the Tevis Mark II, Bosch 3, and Bendix 10 ABS systems. The PowerMaster 3 system has 4 wheel speed sensors. The front sensors are mounted on the spindle assembly and are non-adjustable. Like the Delco 6 system, the front sensor ring is on the outboard constant velocity joint. If damaged, the outboard CV joint must be replaced. Now, it's also important to make sure a replacement CV joint assembly has the proper sensor ring for the application. The rear sensor and ring are an integral part of the rear wheel bearing and hub and cannot be serviced separately. Rear sensors are also non-adjustable. The ABS controller is located inside the vehicle under the passenger seat. The controller provides anti-lock braking once the vehicle speed reaches 2 miles per hour and performs continuous speed sensor checks as the vehicle is driven above 5 miles per hour. The hydraulic modulator unit contains the master cylinder, a pump and motor assembly, a pressure switch, the relief valve and accumulator, 3 solenoids, and isolation and displacement valves for the front brakes. The fluid reservoir contains a level sensor. Many of the components that are attached to the PowerMaster 3 assembly are serviced separately. When the ignition is turned on, the pump motor runs to build pressure in the accumulator for power assist as well as anti-lock braking. A pressure switch causes the pump to kick in when the accumulator pressure drops below 2200 psi and to shut off when it reaches 2700 psi. A relief valve prevents the accumulator from exceeding 3400 psi. The relief valve must be replaced if it leaks. An interesting point to note about the brake system on the cars where the PowerMaster 3 system is offered as an option rather than as standard equipment is the way in which the brake hydraulics are split. On cars with this ABS system, the primary and secondary sides of the brake system are split front and rear, while those that do not have ABS are split diagonally. Now, the PowerMaster 3 system itself is a 3-circuit system. The front brakes are controlled individually, but the rear brakes are controlled as a pair. The Delco Moraine ABS 6 was introduced as an option in 1991 on Saturn, Buick Skylark, and Olds Cutlass Calais, and the Pontiac Grand Am models. It can now be found on numerous General Motors front-wheel drive vehicles, including Chevrolet Luminas and APVs, Chevrolet Beretta, Corsica, and Cavalier, Pontiac Grand Prix, Sunbird, Olds Cutlass Supreme, and Buick Regal. The Delco 6 system found on this growing list of vehicles is an add-on or non-integral type of anti-lock brake system with a conventional master brake cylinder and power booster.
Delco 6 ABS has 4 wheel speed sensors. The front ones are mounted on the steering knuckle assembly. The sensors are non-adjustable, so there's no air gap adjustment to make if a sensor has to be replaced. The sensor rings for the front wheel speed sensors are on the outside of the outboard constant velocity joints, which means the CV joint has to be replaced if the sensor ring has been damaged. You must also make certain the outboard CV joint has the correct sensor ring for the application you're replacing. An unusual feature about the front wheel speed sensors on the Delco 6 system is that they're made of plastic rather than stainless steel, as is used in most other ABS applications. This lowers the manufacturing cost of the system, but also makes the sensors a bit more vulnerable to damage by careless handling. Never pound on one of these sensors or attempt to force it into place. The sensor should slide right in. If it doesn't, check for obstructions. The plastic sensors do not need to be coated with a corrosion-inhibiting lubricant prior to installation. The wheel sensors are connected to the main wiring harness by a jumper harness made of highly flexible twisted pair wiring. The wires are twisted to reduce radio interference. Their flexibility also allows them to handle the motions of the suspension. If the sensor wires are broken, loose, or damaged, replace them rather than trying to repair them. Soldering, splicing, or taping can come loose as the wires flex with the suspension. The rear wheel speed sensors and sensor rings are located inside the rear wheel bearing and hub assemblies and can only be replaced as a complete assembly. Rear sensors are also non-adjustable. The brains of the Delco 6 ABS system is the electronic controller. It is not serviceable and must be replaced as a complete assembly. You'll find it located on the firewall in the engine compartment. Located inside the controller will be a quad driver module. Its purpose is to control the operation of the warning lights and enable relay. It also helps protect the controller against damage in the event of accidental probing. The controller monitors wheel speed through the 4 wheel speed sensors during braking and modulates braking action as needed to prevent wheel lockup. A switch on the brake pedal signals the controller when the brakes are being applied. Power to the ABS system is provided through the ABS Enable relay when the ignition is turned on. The relay is located under the hood in the relay cluster. The Enable relay switches power to the DC motors, isolation solenoids, and electromagnetic brakes. 2 warning lights are used on the instrument panel. The amber ABS light signals the driver when the ABS self-diagnostics has detected a fault which might cause the controller to disable the ABS system. The other lamp is a red brake light that comes on when the parking brake is applied or if the hydraulic pressure has been lost in either the primary or secondary side of the brake system. The master cylinder is a compact tandem design with a vacuum power booster. The brake systems on General Motors front-wheel drive cars are split diagonally, so the primary or rear master cylinder piston operates the right front and left rear brakes, and the secondary or front piston operates the left front and right rear brakes. The master cylinder is aluminum and is not rebuildable. If defective, it must be replaced as an assembly. Attached to the master cylinder is the hydraulic modulator and motor pack assembly. The modulator is held by 2 banjo bolts at the master cylinder's 2 upper outlet ports and 2 transfer tubes at the 2 lower outlet ports. An important service point to note here is that the 2 lower transfer tubes and O-rings must be replaced if the master cylinder and modulator are disconnected from one another. This is necessary to prevent leaks that could cause the brakes to fail. The modulator assembly consists of fluid chambers for all 4 brakes, 4 internal check balls, 2 isolation solenoid valves, a motor pack containing 3 bidirectional direct current motors with electromagnetic brakes, or EMBs, and/or expansion spring brakes, ESBs, 3 ball screw assemblies, 4 pistons, a gear drive set, and gear cover. The modulator, a motor pack, the isolation solenoid valves, the gear cover, and individual gears are all serviceable parts and can be replaced separately. The hydraulic modulator and motor pack assembly on the Delco 6 system is totally unique from the modulators used on other anti-lock brake systems. The modulator contains 2 isolation solenoid valves to block off the front brake circuits when anti-lock braking is required. But there's no isolation solenoid valve for the rear brakes. One isn't needed because the rear brakes on front-wheel drive vehicles do very little work anyway, handling only about 20% of the vehicle's braking effort.
Kelsey Hayes rear-wheel anti-lock brake systems have been in use since 1987 on Ford F-Series trucks, as well as later model Ranger, Bronco, Bronco 2, and Explorer trucks, and Aerostar vans. Now, Ford calls their version the rear-wheel anti-lock brake system, or RABS. On General Motors applications, it's called the rear-wheel anti-lock, or R-wall system. You'll find it on 88 and later Chevrolet C and K Series pickups, on 89 M Series Astro minivans, and S and T Series pickups, some S Series Blazers, and on 90 to 92 R and V Series light trucks and G Series vans. Dodge has also used the R-Wall system since '89 on its D and W 150 through 350 series Dakota and Ram Charger pickups. A new zero residual pressure rear wheel anti-lock, or ZP R-Wall system, has been added on 92 3500 HD models C and K series GM trucks. Now, all other 92 C and K series truck applications still use either the R-Wall or the 4-wall system. The new ZP R-Wall system works in essentially the same manner as the R-Wall system, but components are not interchangeable. The ZP R-Wall system is designed to handle the larger volume of fluid that's found in the rear disc brake calipers on the 3500 HD models. The electronic controllers for the R-Wall and ZP R-Wall systems look similar, except for a gray electrical connector cap on the ZP R-Wall controller compared to the black connector cap on the R-Wall controller. The barcode designations also are different, with a Z and R distinguishing ZP R-Wall from R-Wall. The two controllers, however, are not interchangeable. The Kelsey Hayes RABS, R-Wall, and ZP R-Wall systems are non-integral rear-wheel only anti-lock brake systems. The conventional master brake cylinder and power booster supplies brake pressure to a dual solenoid control valve for the rear brakes. This unit contains only 2 solenoid valves, an isolation valve to block pressure from the master cylinder to the rear brakes during anti-lock braking, and a dump valve for relieving pressure. The dual solenoid control valve also contains an accumulator for storing fluid pressure during the dump or release phase of operation, and a reset switch which allows the system to maintain proper brake pressure. The electronic controller that regulates the operation of the solenoid valves is separate from the control valve and is located next to the master cylinder on some applications. On Dodge trucks, you'll find it on the passenger side cowl panel under the dash. On Ford Bronco 2s, it's located under an access panel by the driver's door pillar. The controller receives a speed signal from a single vehicle speed sensor. On Ford and Dodge applications, you'll find the speed sensor in the differential. The sensor ring is on the ring gear. On GM applications, the speed sensor is located in the transmission tail shaft, and the sensor ring is on the transmission output shaft. On GM vehicles, fault codes can be retrieved manually or with a scan tool. Now, both methods use the ALDL connector. The manual technique involves jumping terminals A and H, or grounding terminal H. After grounding terminal H, 20 seconds or more may elapse before the code starts to flash out. On Ford and Dodge trucks, the fault codes can be retrieved by manually grounding the diagnostic connector and counting the flashes of the amber ABS light. Let's review for a moment the manual procedure for reading fault codes on these systems. Now, the flash code sequence for Ford, GM, and Dodge, as well as import truck rear-wheel ABS systems, is the same for all applications. But it does differ from the sequences used on other ABS applications, so pay close attention as we demonstrate it.
The difference is the way in which the flashes are counted. Start counting from the last long flash. That's 1. Then add the short flashes that follow. The total is the corresponding fault code. For example, start counting when you see the last long flash. Now, add the following short flashes. 1 plus 8 equals a code 9. The code will repeat, so read it at least 3 times to make sure you count it accurately. Remember also that Kelsey Hayes rear wheel anti-lock systems can only store 1 code at a time. To complete your diagnosis, therefore, you must first fix the original code, then clear it, then test drive the vehicle to see if any additional codes appear. If the brake light comes on again, you'll have to repeat the readout and repair sequence until the system has been completely repaired. To manually clear a stored fault code on GM and some Dodge trucks with R-Wall, remove the appropriate fuse or disconnect the battery for 5 seconds. 4 revs will clear once the ignition is turned to the off position. To manually clear stored codes on 92 GM vehicles equipped with the ZP R-Wall system, follow these steps. 1. Turn the ignition off. 2. Pull the stop hazard fuse. 3. Turn the ignition on. If there are any additional faults in the system, the brake warning light will remain on. 4. To clear these, jump terminal A and H on the ALDL connector or ground terminal H for 1 second. 5. Remove the ground for 1 second. 6. Ground terminal H again for 1 second, and this should turn the brake light off. 7. Turn the ignition off and replace the stop hazard fuse.
The Tevis Mark IV anti-lock brake system is an entirely new system and is different from the earlier Tevis Mark II system. It first appeared in 1990 on the Lincoln Continental and Ford Taurus SHO. It was also offered as an option on the town car. Since then, it's been added to such vehicles as the Ford Taurus and Mercury Sable and the 92 Crown Victoria and Grand Marquis. General Motors also adopted the Mark IV system in '91 for its Buick Park Avenue and LeSabre, Cadillac DeVille, Pontiac Bonneville, and Oldsmobile 98, 88, and Royale. The Mark IV system is an add-on or non-integrated ABS system that uses a separate hydraulic modulator and pump assembly in conjunction with a standard master brake cylinder and booster. The earlier Mark II system, by comparison, has an integral ABS modulator, pump, accumulator, and master cylinder in its hydraulic control unit that uses brake fluid stored under high pressure in the accumulator for power assist and anti-lock braking. The Mark IV is a 4-circuit anti-lock brake system. Although there is a separate solenoid for each wheel in its hydraulic modulator assembly and an individual speed sensor for each wheel, both rear wheels are controlled during ABS braking as a single output with separate feed lines. On applications where traction control is offered, the solenoids can be used to provide independent braking for either rear wheel. Let's now look at the components in the Tevis Mark IV system.
The master cylinder is a conventional tandem design with a conventional vacuum power booster. The brake system is split diagonally, so the primary or rear master cylinder piston pumps fluid pressure to the right front and left rear brakes, while the secondary or front piston operates the left front and right rear brakes. The master cylinder is not rebuildable and must be replaced as an assembly if defective. The cap and reservoir can be serviced separately, however. The cap on the fluid reservoir on Fords with Tevis Mark IV contains a fluid level switch, which will illuminate the red brake warning lamp if the level becomes too low. The reservoir also contains a low-pressure hose that supplies brake fluid to the hydraulic modulator mini reservoir. You'll find the hydraulic modulator located in the front of the engine compartment. Ford service literature refers to it as the hydraulic control unit, or HCU, while General Motors calls it the pressure modulator valve, or PMV assembly. To avoid confusion, we'll simply refer to it generically as the modulator assembly. The modulator consists of a valve block manifold with 4 inlet and 4 outlet solenoid valves, a pump and a motor, and a mini fluid reservoir with a fluid level indicator. An indicator is needed because the reservoir is sealed and cannot be checked manually. If the fluid level is low for any reason, the amber ABS warning light will come on and the ABS system will be deactivated. But a fault code may not be set for this particular condition. On vehicles with traction control, the modulator is larger and contains 2 additional isolation valves, 1 for each front wheel. The isolation valves close when the traction control function comes into play to prevent application of the front brakes. The valve body, pump, and motor and reservoir on the modulator assembly can all be serviced separately. Other than seals and gaskets, however, no internal parts can be serviced. The brains of the system is the electronic controller, which is usually referred to as the Electronic Brake Control Module, or EBCM, in both Ford and GM service literature. On some vehicles, such as the Lincoln Continental, the controller is located in the rear of the trunk compartment. On other applications, you'll find it located elsewhere. The controller monitors wheel speed continuously through its 4 wheel speed sensors, which are mounted in the front knuckles and rear brake rotor backing plates. Front wheel speed sensors on Ford applications may differ in service procedures. Check the appropriate service manual for the correct installation procedure. Rear wheel speed sensors on Ford vehicles also have differing installation procedures. Some vehicles, like the Lincoln Continental, need a special tool, T88P-5310-A, to lower the suspension arm to remove the rear sensor. Be sure to check the appropriate service manual. If the vehicle is equipped with an air suspension system, be sure to deactivate it before the vehicle's wheels are lifted off the ground. There will usually be an on-off switch in the trunk for this purpose. All wheel speed sensors on GM vehicles with Tevis Mark IV systems are not adjustable. The controller also receives additional input from a brake pedal travel switch mounted on the brake pedal. Its purpose is to provide feedback about pedal travel. The switch is normally closed, but opens when the brake pedal is depressed beyond 40% of its normal travel range. This action signals the controller to energize the pump in the modulator assembly, which then pumps brake fluid back to the master cylinder. The pedal then rises until the switch closes, at which point the pump is turned off. This process maintains proper pedal feel during ABS stops and prevents the pedal from sinking too far toward the floor. The driver may hear some noise while this is occurring and feel the pedal pulsate and rise, but this is the normal way in which the system operates. It should be noted that proper adjustment and operation of the brake pedal travel switch is very important. If not correct, the driver may notice objectionable pedal feel during the entire ABS stop. The pedal will become very firm, pushing the driver's foot up to an unusually high position. There's also a pump motor sensor in the modulator assembly that signals the controller when the pump is running. If the pump runs excessively and the brake pedal switch remains open, the controller recognizes that something is amiss and sets a fault code.
Over the years, there have been many improvements in the tools used by law enforcement professionals. These improvements have been seen in many areas, from communications to weaponry. Another law enforcement tool that has seen many changes is the police vehicle itself. 1991 marked the beginning of a new era of safety and enhanced performance for these vehicles, with a wider introduction of anti-lock braking systems, or ABS. This informational program will acquaint you with ABS, how it works, and more importantly, the safety advantages it provides the police officer. Statistics provided by police agencies across the country show that many accidents occur in situations where vehicle control is lost due to wheel lockup during sudden or hard braking conditions. Conditions that many police officers must be prepared to face daily. In order to understand the anti-lock brake system, let's first look at a conventional brake system that has been in use for over 50 years. When pressure is applied to the brake pedal, the system applies force to all brakes simultaneously. This is today's brake system with the ABS feature. It is designed to help keep the vehicle wheels rotating as the brakes are applied and assist the driver in achieving a controlled stop. With ABS, sensors monitor how fast the wheels are rotating, continuously feeding this information to an onboard computer. In a braking situation, if the computer determines that a wheel is about to lock up, it sends a signal to the hydraulic modulator to automatically adjust brake pressure several times a second as required. This allows the driver to retain steering control while providing a higher braking force on most surfaces than a locked wheel provides. ABS is an added feature to a brake system. In the event that the ABS feature is disabled, the vehicle will continue to have use of its conventional brake system. In the next few minutes, we'll look at some demonstrations that were developed from input by police officers across the country. These demonstrations were done with an active state police vehicle with 5,000 miles on it. The demonstrations were conducted at the General Motors Proving Grounds in Milford, Michigan. The drivers are state police officers. Their demonstrations will highlight the enhanced control features of an ABS-equipped patrol car. The officer's first demonstration will be stopping on a wet surface from a speed of 50 miles per hour. First, without ABS. Now, with ABS. It is important to point out that during an ABS-assisted deceleration, you'll feel a noticeable pulsation or vibration of the brake pedal. This is to be expected and is an indication that the brake system is in the ABS mode of operation. Here, the driver will attempt to stop while negotiating a tight curve at a speed of 85 miles per hour without the aid of ABS. Here, he'll attempt the same stop at 85 miles per hour with ABS. As you can see, with ABS, the officer is able to control his steering while braking in the curve. Here is a similar situation faced by officers in rural communities, stopping on a gravel surface from a speed of 60 miles per hour without ABS. Now, with ABS. Now, an officer will demonstrate stopping on an irregular surface with the ABS feature. The vehicle's speed is 50 miles per hour. In certain circumstances, such as going over a series of bumps or railroad tracks, with the brakes applied, ABS-equipped vehicles may decelerate more slowly. If this happens, maintain full brake pressure. Never pump the brake pedal. The next demonstration highlights the enhanced directional control of an ABS-equipped police vehicle. In this case, last-second instructions for a right or left turn are radioed to the officer as the vehicle approaches an obstruction at 50 miles per hour. First, without ABS.
Left.
Now, with ABS, again at 50 miles per hour.
Right.
ABS allows the officer to steer around the obstruction while braking. The officer will now demonstrate a series of high-speed panic stops from speeds of approximately 100 miles per hour. On this first run, he will attempt a panic stop without the use of ABS and will try to avoid wheel lockup. He will now attempt the same stop with the aid of ABS. Here, the officer will try the same panic stop without the aid of ABS, attempting full wheel lockup. It is important to note the extreme tire damage caused during this stop without ABS. To further emphasize how ABS adds to vehicle control by allowing drivers to steer in a hard braking situation, Let's look at a panic stop while trying to avoid an object in the road at a speed of 50 miles per hour. First, without ABS. Now, with ABS. This example simulates stopping with the right tires on dry pavement and the left tires on ice from a speed of 50 miles per hour. First, without ABS. Here, with ABS. As you can see, the ABS feature allows the officer to maintain control of the situation. An example of this in the field is stopping half on a gravel shoulder and half on pavement. The vehicle speed is 60 miles per hour. We did not attempt this stop without the aid of ABS. As you've seen, ABS improves the officer's ability to better control the vehicle during hard braking situations by providing improved steering control and, in many cases, shorter stopping distances. ABS does not, however, overcome the laws of physics. Stopping distances and vehicle control are functions of road surfaces, tire condition, vehicle speed, steering inputs, and other factors. We hope that this program has provided you with a better understanding of why ABS was developed and how it improves the safety of police vehicles.